frequency representations on matrix type operators and feed views for function spaces. So please, Professor.
Thank you. So I will actually continue with my third lecture, which is given in the title. It's a little different, and actually I will follow results which were actually definition which was given by Rangowski, who told about calculi, Hermann calculi, and so even I will repeat many things because this is always important. This is pretty complicated approach. For me, maybe for somebody is not so much, but I think it is. Okay, so as it is written, we will show that in this general case, one can have that randomness and periodicity are equal with some additional assumption in the most general framework of Hermann algebra. Even we will improve results which are known for special pseudo-differential calculus. So I will tell you this later. So I will start with this tau type pseudo-differential calculus. Tau is a real number, and so everything goes in that way. And there is a way how one can go from one tau to another tau, and so I will not talk about that. This is also very well known. So Hermann calculus, which I will mention here, is the one which works with tau equals 0, and then you just lose y, and then you have just Fourier transform. No, actually this is double integral. Yes, this is double integral, so this is okay, just as it is. Let me repeat calculi which exist in this theory. So the first one which I am writing down, did I miss? No, there is. There is phi and phi, big and small one. So this is Biels-Fetterman calculus. Sometimes in some books I will indicate this phi comes to that place and another place is psi. So it depends. So Shubin calculus works with this Japanese bracket. Rho is less than 1, then you have subadditivity, and the weight function is of order n. It gives the order of the symbol. This is Hermann. The rho is less or equal 1, and delta is less than rho. And so you have this. I will come back to all these things again. Maybe this was not mentioned, it seems to me. This scattering calculus, when you have separated the variable x and variable psi in that way. And the wave function is also scattered. It's also global calculus. And so I here just give the well-known composition formula for the Hermann calculus. So if you have two operators in Sm1, so with different weights, then composition of these two operators has a symbol given in this short form in that way. If somebody likes, he can just develop this into Taylor series and then get what it is. and this is how it looks like in the asymptotic expansion, so it's very well known. I will actually talk later about the cross product of these two things, not this one. Okay, so about symbols, and then what we have actually, symbol is elliptic. Always this definition is the same, so ellipticity does is that condition, but of course you have a bound from above, because this A belongs to that space also. This is somehow between C1 M and C2 M from both sides. This is, and then you have this kind of parametrics for A. This belongs to M minus 1, very well known, and S1 and S2 are just regularizing operators, which means that they map S prime into S. And so now I will just recall the definition of Fredholm operator. So if with the notation kernel of A or the set of zeros of A, and co-kernel is just H2 over image of H1, and then this is if they are finite, this is an index of that operator. So I will somehow come to the end of that point. If you have this is good to have this theorem, because if you have T Fredholm and K compact, then you can then you know that T plus K is a Fredholm, and if you have this kind of relation between T in the H1 to this means continuous or bounded operator from one Hilbert space to another one, and S1 the opposite direction, then if these two equalities holds, if somehow S2 is the right parametrics up to compact operator, and S1 is the same but from the left side, then both they have the same index, opposite. They are, all of them are Fredholm. So somehow this is definition, and I will come to that later. Of course, this is very well known, what we always have when we have real calculus, just for remembering again this fact, nothing more. Actually, Bojan told a lot about this and give the right definition of that, why it maps S, because if it is in S, then it maps S prime into S, and then it will map S into S, and so on. So there are some conditions which I will not say. For me, it was interesting because he mentioned yesterday in his lecture quantization, how it works. So, I mean, it's a nice formula for the calculus. So what is the quantization of x psi? This is just this operator. If you have, he mentioned here yesterday, this kind of operator or symbol, and then the corresponding pseudo-differential operator, it has the same, this form, which actually become that one. And so this is a composition, very simple to think that composition of such is this. And then this is what he actually told yesterday, that he has some Poisson brackets, and even if you have opposite, then it's not commutative, but you have similar form. I think that here you have minus, and then you can calculate these things in a quite nice way. And somehow, if you want to look geometrical version of this calculus, if you don't want to be concentrated on one basis, then actually you should use this kind of operators which are free of the coordinate system. And so here you have also these also brackets, you have Hamiltonian flow here and how it works. So just for curiosity, I put this because Bojan mentioned that yesterday, and I found that maybe it is interesting to just repeat these facts here. So in any calculus, what we have actually that if you have elliptic operator, then you have parametrics, and then you have Fredholm property, Fredholm mapping from that space, Hn1, or weights for N1, and its index is independent of N1. So you can
Michael?
start with it. So the question is it true?
They have some
Direction. And this is what we were, Bojan and me, what we have wanted to study. And then, of course, there are many great names you can see who did these things in their own country. Kordesh, Bills, Pfefferman, Schroer. So there are, of course, Hermander, mentioned here. So all these people, these things, and this is, but you will see that in general setting, it's, how to say, much more involved in the theory. So I will repeat inverse closedness again in the following form here. So if we are considering the operator of order 0, this is still classical. And if it is, so this is 0 means that this is function just equal 1. And then if this operator is bijective, whether it is true that the inverse is also a pseudo-differential operator, which means whether it also belongs to the same class. And so this was in the Wave-Hermander calculus, this was done by Boni and Schema with some theoretical assumptions. I will mention them later. So, and this is called spectral invariance. I used this yesterday in completely different context, if you remember, but whatever you, this is always the same. You have inverse operator, whether this inverse operator belongs to the same class as the starting one operator. So if we have mapping, which is of CK class, which means that it is even smooth if k is equal to infinity or just up to order k. Is it true that this operator is in the same class, and of course whether it is also CK mapping, and this is what will be shown in our case, and I will tell you this about that later. now I will say something about calculus. Calculus actually was given in the book of Lerner, and then I went back to RD. But in principle, you can go. You can start with some n-dimensional vector space, and then you should have hard measure on it, and dual hard measure just to save Fourier transform that works well on that space and so on. But so I will have in many slides the notation V and W as a product of V and P. W is actually a product of V and V prime. But here V prime is again RD. So somehow the same thing. And so this will simplify a lot of the notation of theory, because if you don't have, then even you must introduce some bijective mapping from vector V to Rn, which will be known by L, and then there are many, how to say, additional facts, technical, but at least not so easy. So when we have Borel measurable symmetric covariant to tensor field on V, positive definite at every point, then we have Riemannian metric. So we will use this notation. This is quadratic form. Actually, I much more like when this is written as real scalar product of T1 and T2, let me say, or I will show you this later, because somehow you lose, because when you fix one of them, then you are actually in the dual. So it works now on two vectors. But if you fix one, then you are in the dual space. So this is an important fact which is useful, because for symplectic transform we also have the same situation. So, but these details will not be given in my lecture. So this is quadratic form. So we have with every point we have the matrix denoted by Gx. So when you fix x, actually you have just a matrix, and then you can do everything. It's not so, how to say, of course you have to take care about how you will transfer the results from the classical Euclidean metric, where G of, this is just classical scalar product, nothing more. In the Euclidean metrics, but the idea is to change x to go through the whole space W, and then to discuss transfer from one point to another point, and this is a really difficult part. I will show you. This is idea of my talk is actually to show you that this is really far from being trivial. This calculus. Even from the beginning, you found out that from the Borel's talk how it is not trivial. Of course, he's an energetic person. He can jump on that table, but I will just be quite slow. So this is symplectic dual of matrix G, and actually if matrix is if Gx is equal to Gx sigma, then this is called symplectic metric. So this is also, for example, this is very much important in the proof, because for the main theorem this was extremely much used. Of course I will not go in details in the proof, but so let me say again, so this was written maybe 3 times at least, or 3 times on the blackboard, and now here. So we can list it 3 conditions. This is slow variation, which says if points are similar, near. So this is actually ball in matrix X around point X, but you can also think about that this is a ball around in the metric gx around y. Why not? This is just symmetric. And so you have this relation, but this is well known. If you just have a part of this, if you have just this part, then you will get this for free. But you have to change constants which appear r and c, each other. And so this is slow variation, this is temperance when you have, so now t is variable point. And gx sigma is, as I told you, the symplectic dual. And so, but let me say, this was not told. If you want to think about gx sigma, if you take a Jacobian of it, I will tell you something about that, then this Jacobian is actually of polynomial growth. And so somehow this is maybe one explanation why, why additional explanation for that so-called temperance or slow variation. For slow variation and then the temperance. And this condition was really very well explained by Boyan. This is so uncertainty, condition of uncertainty, that this must be greater than this one. Actually, gx sigma is also Hermander matrix, but calculus with gx sigma is good only for Euclidean. For other situation, this is just you lose almost everything. So, but from a theoretical point, as you see, you always have this g sigma because this is actually polynomial. Let me look in that way, if I can say that. Of course, it is not, but if I want to understand that, I think in that way. So this function, which is inverse of it, is so-called Planck function. So people put 1 over that, 1 over lambda g, this is Planck function, and, but we will work with that version, just, I don't know, it's easy. And strong uncertainty is then on that side you should have some kind of metric condition. In the case of Pfefferman, Bill's calculus, on that place you have 1 plus x squared plus c squared to some epsilon, positive epsilon. But Boyan already told that function phi and big phi should satisfy some additional condition, but at least this one. Okay, I will tell this later. So again the game with how it looks like in metrics. I just want to explain you this. So this is what I like much more than this one, because you see how operator works, and even you can see from here. If you so what is this? This is t1 to the power 2, t power plus t2 to the power 2. 3t3 to the power 2 and so on, over phi of every times over phi of x psi, and then on square. And then when you make a change of variables, t1 over phi of x psi is a new variable, t2 over the same phi of x psi, then you will see that Jacobian is just product of these things. This comes to the power n, 1 over p of x to the power n, multiplied by this 1 over psi x c to the power n. So somehow what Boyan wrote and what I wrote, right? This Jacobian gx absolute value is just this. So this is somehow one has to have some kind of feeling for what is going on in that calculus. And so Hermander did this in that way, very well explained. And so you see, this is what I usually like to use, but actually better version is that I said that people use both notation. This one belongs to Rodino and Nicola, and so since I was influenced by that, but this is really nothing. So, but what is important? You can see how I don't know whether I wrote these on these slides, but how one can find out what is G x psi sigma. This quantity comes to that place, and this quantity comes to that place. So somehow, very let me repeat. So just maybe I wrote it. I forgot what I have on slides. But in any case, so you have these classical things, but it is written down. Sorry, this is written here. Sorry for my explanation. And then you have what is lambda g. This is just that product, which is important for us. And then you see that this must be greater than 1. And then, okay, so let me go further. So I will repeat what does it about function m, which is a weight function. Weight function is somehow should be related to that g, to metrics. And so it is G advisable if you have similar things actually. If you look, so again you can just assume this half and then you get the whole. This is the same as temperance property, but for weights. So I don't know what I wrote. This is again the same thing. It's not so important, maybe just my mistake. Why I repeat the thing. So symbols are actually here. So this is what Boyan wrote and explained what it is. For me, this is differential, total differential for the L, and then I look a little different on that. For me, this is just if you take differential, you know that you have at point you have T1 delta x1 plus T2 delta x2 up to Tk or L delta L, x Lk L, sorry, and then if you just put on the power k and calculate coefficients, you will get what you like also, which is somehow another way of thinking on that quantity. But in any case, so this is a simple class, which will be of course important. And what is the most important in the theory is, after all, always partition of unity in some sense. Partition of unity, of course, everybody knows what is the partition of unity, but if you have just function phi in C0, and let's say positive, compactly supported, if you write phi of x minus y dy, this is actually continuous partition of unity. If, of course, if integral of phi of t dt equals 1. Nothing more. So for the classical, for the Hilbert structure, it's really trivial, but here it is very difficult notion. So we have, I mean, this was done by Herlander, but explained later by these people, Boni, Shema, and Werner, and some other people. So this is confinement. Actually, confinement means you should not, this is for me always somehow partition of unity, but not of unity. You can have just property, I mean, this integral should not be equal to 1. It can be equal to any constant, but you can divide it. What is important that this is somehow non-degenerate, and so this kind of assumption will be somehow involved in this talk. So this is a ball. This is just a ball, and then you see that we say that a smooth function over V is Gx confined in UXR if this holds. So again you have this derivative, but you have this factor. And now if you fix x and r, and if you just think about that this is polynomial, you immediately get that this is S. And this is true, and this is written. For fixed x and r, the set Gx confined symbol in UX coincide with S of B. Test first test function space. So somehow good way of thinking. And so what one expects. So let me. So a family is confined. So now I'm talking about family. So you see that X goes through W, and so somehow this is phi sub X is actually a function of Y. Sorry, of Y. And so when I write just phi, maybe somewhere I will write just phi, one should think that this is not a function of one variable. This is function of X, but this is parameter in that case, and it's a function of Y. So this is the condition which already was told by Boyan. So one should have that this is a uniform. I mean that the same constant holds for every x in that context. And so now that the question is whether we have such family, and I will talk about that. But of course, what we have. If suppose this is a prime, so there is a uniform in G confined family such that supports are in that UXR. So this is important condition which we will always have in mind, and you see that this is partition of unity. And somebody he explained yesterday why this is volume element, that it is not changed. Just if you just cancel this part, you will have just integral of a gx to the power 1/2 dx, and you have here ball. And if you remember my change of variable just will give you the integral over ball, the Riemannian integral, Euclidean integral over the ball, and this is just volume over ball. So nothing more is inside. So this is gx dx. This is the volume density induced by G. Okay, so let me go further. So we have fresh structure. If f. No, this is just definition of measurability, strong measurability. I will skip this part. Actually, I mean, in the whole theory, in papers of Bonish, Ema, and Barnell, they somehow skip this. They have always y minus x, not the distance between point and ball. And then this, even if we start with the function from x to gx, which is measurable, then we can show that this is measurable. And lot of work actually is done for these measurability questions, and I will skip all of them. And so, in order to show how this calculi is, how to say, technically heavy, I just like to show, and sometimes it is really important. If one wants to do anything in that field, one should do this by himself to find out what does it mean. So you see, although this is written, this is the second condition. This is reference, but you see that here we have plus minus. This is what Bojan already wrote immediately, but you see that somehow constant is different. Here, our is different. And so, but only not this, it's not actually, but you, if you remember, you should have here y minus x, and here is u of xr. So somehow this is not the same. I just compare these things, but they are not the same. And so there are many such kind of inequalities which are, how to say, one should be really extremely careful in doing these things and applying all of them, because that is, for example, convergence, question of convergence. dvg is just dx Jacobian absolute value of gx to the power 1/2 times dx. So this is dv. Maybe it was written earlier, I don't know. But in any case, this is what I told. So somehow there are a lot of such results. Even next slide contains such relations between, let me say, Jacobians, and so you always have these, and you can immediately see that these things hold. If you follow what I told about how I make Jacobian to the power 1/2, of course, it's not important, then you can see that this is 1. And so this is, of course, you should show that this Jacobian is invariant under transform from one basis to another symplectic basis. So somehow this is also shown in our work. And so there are many such kind of inequalities you see, and they are very, how to say, very much used in the calculus. So you should always, you should feel them and then put them on the right place. Even if you, so for example, if you don't have smoothness, which is actually in the calculus, you can, if you consider a confined family, you can start with measure function from x to g, phi x, let me say, and then, but always you can, even for metrics or also for weight function, you can change that measurable one with the smooth one, but sometimes it is not possible if you do not have differentiation. Or so, for example, this result shows if you have just function which satisfy that condition. So you see, this is the same condition as for the confinement or for confined family, but without derivatives. And so you see, you have this, here is x, and you have, from that you get this one. This is the same, but you have a new factor. You have new factor, this one. And you can see that this factor is somehow completely different than what is written here. This will give you, actually, if you have integration with respect to y, you have this new factor, which was quite important. And so on. So there are many technical things in that calculus. And so let me come back to confined family, because I will repeat. Okay, I will not repeat the construction, but just mention it. So you see, when I write this, this is function of two variables. This is what I already told. Then we so on that place, as they did, we follow. They put x here, but x should be down. It is much more useful if you have x down, and then you leave this place for variable y. But in any case, so this is definition, and this is vector space. So this is the whole family of such functions which satisfy these, and so of course, because this explains because of measurability of this function, you have these rights to write supreme norm on the right hand side. So what I already told, the one condition from below should be satisfied, that this infimum is greater than 0, because we will take 1 over phi of x. So so I am a little out of my talk, not because in the talk about ellipticity and transformers, which will be in the end, of course, there are so many technical details. If I would start from that point, somehow this is, I think, pretty difficult. But in any case, so we have this relation between confined spaces, and we have properties. What is the product of two product with the symbol in S1G, and so always you are again in the confined family, in the confined space. So this is a fresh algebra, topological model over the fresh algebra. This is just because of these products. This is product and this is model property. And so somehow we have all these properties, and we write down this quantity. This is integral of the whole thing, and actually this is symbol of order 1. This is symbol of order 1, and then if we have non-degeneracy, then again we have 1 over I with index phi to the power 2 is in that class of symbols, and with this is usual product. Okay, so this is what already Boyan told, and somehow very good example how one constructs actually this confined family, but the best one. So this one, which is always used, is the best one. Only what we discussed and what we showed, that actually you do not need to do all the things with the same, with one just representative. Of course, you have many of them, but even if you lose some of the properties. Okay, now I'm slow too much. Okay, so in any case, so this is definition which was given by is it here? Yes, here. So this is what Boyan wrote here. This is actually from the Lerner book, but probably it was done by Boni Shema or Boni Lerner, I don't know who did it. So this is construction. Even you can construct it that this integral is equal 1. And what we would like to have, not only these properties which I already mentioned, but this one also. And the example which I show in some moment we had to use, you have here, you have this function of two variables, x and y, and you can differentiate in both, and then you can get something which is well estimated. So now I come back to that sharp product, and this is what already I told, but this is somehow novelty in the paper, so we consider is Hausdorff locally compact topological space, and then you have this mapping E contains lambdas, and so we are looking for functions which are in CK, where K even can be infinity, and we have this Leibniz rule for the action of a vector field on that sharp product. So this is this also depends on lambda, and then you have one more variable, and you want to see whether it is CK class and not or not. And so now I come to Sobolev spaces. Usually this was done in that way. Sobolev spaces do not depend on operator A, although always we define with A, we define Sobolev space if it is elliptic. But it depends on them, and you can change. So for if A and B, if you take another pair, you will get the same Sobolev space in the usual way. And this is in all these special calculus. This is just in L2 over Rn. I will now tell you how it looks like in Hernandez calculus, but before that, as it was taught, you can localize. So you have symbol, and then if you multiply by partition of unity or confined family, then actually this becomes that quantity. You see that every one is multiplied by this, and then you have integration with respect to y1 and y2. So you have this kind of product. So forget this. This is just multi-dimensional case which I wanted to skip. So just remember that I'm working with scalar symbols, and so how it is defined. I mean, how pseudo-differential operator is defined in that with partition of unity. I multiply A with 5y, and then just this was used actually by yesterday. So. Or we told. But in any case, this has sense in the Bochner and in 0.5 sense also. But now this is Boni or Lerner, Boni Shema definition of Sobolev space. First of all, it's a little strange how it is done. So so for every, let me say, partition of unity, you make this kind of two new partitions of unity, so you can make this. This is important. I think this is Toft who did it. Even in the book it was written. And so somehow Sobolev space is now defined with this function, but you should know U is in S prime, and since theta Y is in S, this is regularization, this is well defined object. And so somehow this is, and then now you see that there are no two differential operators. This comes from partition of unity, and M is important, and you have this kind of product. Of course, one should ask why theta, why not psi, but why not phi? Why? It's true. This is just definition with this started as a starting point, and then the theorem says that you can use any partition of unity, not connected with. But this is somehow important in the proofs. Even when you want to prove, I think it's written on the next slide. Maybe not. Yes, it is written. So H1G is just L2. But in order to prove that fact, you have to spend a lot of time. This is absolutely non-trivial thing. So somehow there are many, danger places where one should think much more about what is going on. And so this is, you saw that so this is a continuous mapping from that space to another one. If this is bounded from below, then this is continuously included in HM2 of G, and so on. Now I will come to electricity again, and probably finish the talk. So this notion is important, geodesically temperate. So this was done by let me say Bonnie, leader of that group, Bonnie Ladle or Serbia, I don't know. So this is so-called geodesical temperate, and this was done for this intermediate matrix, which is defined by G equals to square root of G times G sigma. And this is also symplectic. This is geometrical mean value of, so somehow very important thing for the proof. And so now I will come to the end, but there is one place which maybe in the end I will tell this. So let me say what is the theorem. So if you have geodesically tempered Fermat matrix, EE and E is house of topological space, then you can speak about continuity for every lambda, and then you have if you have invertibility, then you have actually continuity with respect to lambda. So you have this what to say. So if it is invertible, so you have inverse for everything, but this is continuous. This is important as well. This is continuous from E. If this is in Cn, again, this inverse is again in Cn and can be infinity also. So this is important theorem. And so there are key Riemann theorem. So if you have a Hermann metric satisfying this condition, so this is less than strong uncertainty. So this is novelty, even for the classical calculus. And M is G admissible, which means that it is in a good relation with the metric. So if, as it is written, if S is elliptic, and one has M1 also generalizable weight. Then A omega restricts to threshold operator on Sobolev spaces, and its index does not depend on M1. So this is one theorem. Another is the corners. So this is the answer. So you have geodesically temperate Hernandez matrix satisfying this additional condition. So this is, as I told, I will not repeat. So if, again, you have advisable M1 and then weights, and if A in that space restricts to a Fredholm operator, then it is elliptic. So this is the answer, but in the most general case. So somehow, now here I mentioned what is strong uncertainty, which I announced at the beginning. When this is G is 0, this is just scalar product. This is just scalar product because down, if you look, I mean, not always, but if you look in Federer-Beers calculus, you have this 1 over phi to the power 2 and 1 over big phi to the power 2. When you put 0 there, you will just get on both places 1. So somehow this is a clear condition, and so then you have what I already told, this strong uncertainty. So then one has the Dossel-Hernandez integral formula, which will be written on the. So they gave this formula, and what was important that one can show, we show that actually it works in our situation. No, yes, I will see. Only here is remark that results is not the same as in Hernandez because of orientation, which is somehow different. So if we have this strong uncertainty principle and ellipticity or this weight m, and so if you have D, here is D, any compactly properties embedded submanifold of codimension 0 with boundary omega. So boundary in W, which contains the interior of the set where A is not invertible, then index is that quantity. The condition on D is the one induced by V. You see what is V, what is D, what is a boundary of it. And so somehow with the classical result, the just difference is somewhere plus or minus, nothing more. And so this is what Bojan already mentioned here, example of an operator which is not elliptic in any of calculus. And probably this was somehow important for the paper that we have such kind of very, very, very natural symbol, almost s equal to minus 1/2. One gets a harmonic oscillator, but s is between 0 or 1, so it's positive, not negative. In any case, so with this matrix and this AM, which is the A, then one has that it's threshold, and so with index 0. And somehow this is just this an isomorphism if you have this condition, then it's already isomorphism. I wrote this reference of that paper because in the end I will not talk anymore, but just give one small comment. Maybe we send this to Lerner, who wrote the book, because in preparation of that paper we used a result of the book, two results of the book of given in Lerner, but also given in the paper of Boni and Shema, and Boyan is, I don't know how one can do this, but he never give any chance for the mistake. So he found out a mistake in the proof. And so this was, I mean, of course we didn't say this in that way in our paper, we just say, this is true that the assertion given by in the books or papers is true. Result is true, but proof it was not completely correct. But Lerner accepted this. I mean, in any case, this was a good point to have this fact that somehow. And if I would tell you how these two lemmas look like, then I should have maybe 4 more slides just for formulation, not for the proof. Proof is very difficult, very hard. So one can see this. I think that, I don't know whether, I think, Brian, is it true that it appears or is
yeah, it's already published.
because we did this in 2020, and it was accepted in 2020, but this is journal of Jussier, mathematical journal. Jussier, he is working there, and he's editor of that journal. Okay, so thank you very much for your.
Thank you very much, Professor Pilipovic. Maybe someone has comments, questions? If not, then just thank again Professor Pilipovic. So we have 15 minutes break. And
Michael, I wrote you a letter.